Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. From the last session, we gained a better understanding of different number systems. We had a discussion on binary, octal, decimal and hexadecimal number systems. Digital devices usually receives input in decimal format, but computation is actually done in binary. This requires conversion between decimal and binary. Programmers use hexadecimal number system to code for microprocessor. Again, it is to be converted to binary for computation. The same data appears in different format for different purposes. So, conversion between number systems is essential to learn more about digital computing. In this session, we are going to learn conversions between various number systems. First of all, let us understand how to convert a number of another base to a decimal number. The procedure is: first step, determine the positional value of each digit. Then multiply the obtained positional values by the corresponding digits. And the last step, calculate the sum of these products. For example, consider the number 4706 to the base 8. The positional values are multiplied with the corresponding digit, and we get 4 into 8 cube plus 7 into 8 square plus 0 into 8 raised to 1 plus 6 into 8 raised to 0, which is equal to 4 into 5 12 plus 7 into 64 plus 0 into 8 plus 6 into 1, which is equal to 2048 plus 448 plus 0 plus 6, which is equal to 2502 to the base 10. Let's practice another problem of different base. Take the number AF4C to the base 16. As the question is in hexadecimal format, first replace all digits from A to F to its decimal equivalents and then continue. In this example, the binary equivalent of A is 10, F is 15 and C equal to 12. So, AF4C to the base 16 can be written as 10 into 16 raised to 3 plus 15 into 16 square plus 4 into 16 plus 12 into 16 raised to 0, which is equal to 10 into 4096 plus 15 into 256 plus 4 into 16 plus 12 into 1. And the final result is 44,876 to the base 10. Using the same procedure, numbers represented in any number system can be converted to decimal. Let us consider the decimal equivalents of two numbers 215 to the base 6 and 215 to the base 7. They are 83 to the base 10 and 110 to the base 10. Though the digits are same for both numbers, their decimal equivalents are different. When the digits are same, number with larger base yields to larger decimal value. Next, we will see how to convert a decimal number to a number of another base. The method we follow here is known as division remainder technique. As the name indicates, we keep on dividing the number by storing the remainders aside. The process ends when the quotient becomes 0. So, the first step is divide the decimal number by the base value. Then record the remainder from step 1 as the rightmost of the new base number. Then in step 3, we divide the present quotient by the new base and record the remainder as the next digit of the converted number. And in the last step, we repeat step 3 and 4 until the quotient becomes 0 in step 3. The last remainder obtained will be the most significant bit of the new base number. To illustrate, let us consider the number 953 to the base 10. You have to convert this to its corresponding octal number. This is to convert the decimal number to base 8, that is octal. So, we have to divide the number by 8. So, 953 divided by 8 yields to a quotient 119 and a remainder 1. The remainder is stored. This is going to be the least significant bit of the result. Again, divide 119 by 8, we obtain 14 as the quotient and 7 the remainder, which is again stored. Then divide 14 by 8, you get the result as 1 and the remainder 6, and again divide 1 by 8, we get the quotient 0 and the remainder 1, and now the quotient is 0, so we stop the process. While dividing the number, we have noted the remainders from top to bottom. Now read it from bottom to top. 1, 6, 7, 1. We get the octal equivalent of the number. Hence, 953 to the base 10 is equal to 1671 to the base 8. The same procedure is applied to convert any number of base r to decimal. To convert to hexadecimal, be careful, because if the remainder is greater than 9, we have to use hexadecimal digits. Let's practice one more problem from decimal to binary. Here the number is 137 to the base 10. Divide by 2, we get the quotient 68 and the remainder as 1. The remainder is stored. Again divide 68 by 2, we get the quotient 34, remainder 0. Then again divide by 2, the quotient is 17 and the remainder is 0. In the next step, quotient is 8 and the remainder is 1, and next quotient is 4, remainder is 0. Next quotient is 2, remainder is 0. Again divide by 2, we get the quotient as 1 and the remainder as 0, and again when you divide by 2, we get the quotient as 0 and the remainder 1. And when the quotient becomes 0, we stop the process. Again we start writing from the bottom to top the remainders. So, we get the result as 137 to the base 10 is equal to 10001001 to the base 2. This method can be used to convert a number from decimal to any other base. The next is the conversion of a number of base other than 10 to another base other than 10. In this method, we have to convert the original number to a decimal number base 10. Then in the next step, we convert the obtained decimal number to the new base number. For example, convert 4706 to the base 8 to base 16. In the step 1, we convert it to decimal. 4706 to the base 8 is equal to 4 into 8 cube plus 7 into 8 square plus 0 into 8 raised to 1 plus 6 into 8 raised to 0, which is equal to 4 into 5, 12 plus 7 into 64 plus 0 into 8 plus 6 into 1, which is equal to 2048 plus 448 plus 0 plus 6, which is equal to 2502 to the base 10. Now, the octal number is converted to its corresponding decimal. Then, in step 2, convert from decimal to hexadecimal. To convert to hexadecimal, we divide 2502 by 16, resulting a quotient as 156 and remainder 6. This remainder 6 is going to be the rightmost digit of the hexadecimal number. Again divide 156 by 16, the quotient is 9 and the remainder is 12. Our target is hexadecimal value, so convert 12 to its corresponding hexadecimal digit, that is C. Dividing 9 by 16, we get the quotient as 0 and the remainder 9. Now read the remainders from bottom to top to get the hexadecimal equivalent. So finally 9C6. So 2502 to the base 10 is equal to 9C6 to the base 16. So the final result is 4706 to the base 8 is equal to 9C6 to the base 16. A shortcut method is also suggested to convert numbers between binary, octal and hexadecimal. Let's see how to convert a binary number to its equivalent octal number using shortcut method. The first step is to divide the digits into groups of 3 bits starting from the right. Then convert each group of 3 binary digits to equivalent octal digit. I will do one example. 110, 1011, 1101 to the base 2, which is equal to which octal number? We have to convert this binary number to its octal equivalent. First, we divide the binary number to groups of 3 bits from right. The leftmost group has only 2 bits, so add zeros at the left end to make it a group of 3 bits. Next step, convert each group of binary digits to its octal equivalent. So the first group 011 gets a 3 value, 010 its octal equivalent is 2, 111 octal equivalent is 7 and for 101 octal equivalent is 5. Hence, we get the result as 110101 11101 to the base 2 equal to 3275 to the base 8. The next is the reverse of this shortcut method for converting an octal number to its equivalent binary number. The reverse process gives the answer. In the first step, convert each octal digit to its equivalent binary number with 3 bits. Then combine the binary groups. For example, find the binary equivalent of 574 to the base 8. What is the first step? Convert each octal digit to equivalent binary number with 3 bits. So 5 is converted as 101, 7 111 and 4 100. Then combine the binary groups 101, 111, 100 to obtain the result. Hence 574 to the base 8 is equal to 101, 111, 100 to the base 2. Similarly, we can use shortcut method to convert a binary number to its equivalent hexadecimal number. The difference is, in hexadecimal we take groups of 4 bits. So in the first step, we divide the digits into groups of 4 bits starting from the right. And in the second step, convert each group of 4 binary digits to corresponding hexadecimal digit. Convert the binary number 11010 111101 to the base 2 to hexadecimal. First of all, divide the binary number to groups of 4 bits from right. So the first group is from the left significant bit 1101, next group is 1011, next is 110. The last group contains only 3 bits. So the leftmost group has only 3 bits, so adjust it to 4 bits by adding zeros. Next, convert each group of binary digits to its hexadecimal equivalent. So the first one is 6, next is B, next is D, and hence the result 1101011101 is equal to 6BD to the base 16. The next is shortcut method for converting a hexadecimal number to its equivalent binary number. Reverse of the previous procedure will give the result. Step 1, convert the hexadecimal digit to its 4 digits binary number, and in step 2 we combine all the binary groups to a single binary number. For example, convert A7F to the base 16 to binary. We convert each hexadecimal digit to equivalent binary number with 4 bits. So the equivalent binary of A is 1010, of 7 is 0111, and the equivalent binary of F is 1111. Then we are combining the binary groups to obtain 1010, 0111, 1111. Hence, the result A7F to the base 16 is equal to 1010, 0111, 1111 to the base 2. The next topic is conversion of fractional numbers. Let's learn how to convert any fractional number with base r to decimal. Let's first consider a binary number. Find the decimal equivalent of the binary number 1011.101 to the base 2. This number can be written in its positional notation as 1 into 2 cube plus 0 into 2 square plus 1 into 2 raised to 1 plus 1 into 2 raised to 0 plus then the fractional part 1 into 2 raised to minus 1 plus 0 into 2 raised to minus 2 plus 1 into 2 raised to minus 3. And this is equal to 8 plus 0 plus 2 plus 1 plus 0.5 plus 0 plus 0.125, which is equal to 11 plus 0.625, and the final answer is 11.625 to the base 10. Another problem, find the decimal equivalent of the octal number 217.54 to the base 8. 217.54 to the base 8 can be written in its positional notation as 2 into 8 square plus 1 into 8 plus 7 into 8 raised to 0 plus 5 into 8 raised to minus 1 plus 4 into 8 raised to minus 2, which is equal to 128 plus 8 plus 7 plus 0.625 plus 0.0625, which is equal to 143 plus 0.6875, which is equal to 143.6875 to the base 10. That's the final answer. Conversion of a decimal fractional number to binary or octal or hexadecimal does need a little more attention. Let's do one example, 26.625 to the base 10. We have to convert both integer part and fractional part separately. Integer part can be converted using the division remainder method. So, we get 26 to the base 10 is equal to 11010 to the base 2. What about 0.625 to the base 10? To convert the fractional part, we have to follow the procedure given here. The first step is to multiply the fractional part by the base b. Here the base is 2. Then the second step, record the integer part on the right side. Then continue step 1 and 2 until the fractional part becomes 0. Or we will stop after 4 or 5 digits if it is a recurring decimal. In the example given here, 0.625 to the base 10, we start multiplying by 2. So, 0.625 into 2 is equal to 1.250. Here the integer part is 1 and the fraction is 0.250. So, we store the integer part 1. Again multiply the fractional part by 2. So, 0.250 into 2 equal to 0.500. Here the integer part is 0 which we store and the fractional part is 0.500. Again multiply it by 2, we get 1.0. Here the integer part is 1 which is stored again and the fractional part is 0. So, we stop. So, we have to stop when 0 encountered in the fractional part. So, the result is 0.625 to the base 10 is equal to 0.101 to the base 2. The remainders are written from top to bottom. Hence, the final result is 26.625 to the base 10 is equal to 11010.101 to the base 2. To summarize, The conversions we went through in this module are essential in digital electronics. In most digital systems, we input the data in decimal format, but it uses binary for computation by performing decimal to binary conversion. And sometimes we input using hexadecimal, where hexadecimal to binary conversion is carried out for computational purposes. Always the result is displayed after inverse conversion. The relationship between 2, 16 and 8 is the reason for the common use of hexadecimal numbers and octal numbers. 4 digits of a binary number can be used to represent a single hexadecimal digit, and 3 digits of a binary number can be used to represent a single octal digit. This makes the conversions very easy. Here we stop today. We will continue with binary data representation in the next class. Thank you for watching. See you in the next session. Bye.